Hello and welcome to another lecture. In this lecture we're going to learn about moment force. Moment is very important in civil engineering. This is a basic, you want to learn this in this kindergarten of engineering. Really, it's very important because later on you're going to use in beam design, column design, floor design, and you name it, any application, could be steel or timber or concrete. You're going to use moment to calculate stresses, calculate bending stresses, calculate reaction. It's very important. It's basically a force about a point that rotates about a point. But the best way to explain this, do a bunch of examples to kind of get you going. Let me just show you the PowerPoint right here. Okay, you all seen this before. You have a wrench, and then you want to go ahead and make a turning, and when you put a force on right here, it creates a moment about this point, a turning moment, and basically the force become magnified and become a lot bigger over here. And an equation for it is m is equal F times d. One of the biggest things you want to learn about moment is when you say force times d, very important. The d is the perpendicular distance from the point of rotation to the line of action. So it's a perpendicular distance between the force and where you want to take the moment. And again, you have a lot of application for it right here. And here, looking at this right here, if we have this force P taking a moment about 0.0, it's basically rotating around 0.0. And that'd be a counterclockwise rotation, which we always say is a positive. And then if you come this way and take a moment about 0.0 here, and that'd be a clockwise rotation. And all dependent, the different country may use positive here and negative there, but we're going to use the positive going counterclockwise from here. I hope you're hungry, so let's do some example right here. Let me shut this off. So let's take a look at this example right here. We have this three forces, and we're going to take a moment about 0.0. So let's take a summation moment about 0.0, see what it comes out. But we're going to say, you know what, counterclockwise is positive. Actually, we're going to use this sign language right here. Positive like that. Actually, let's go to a bigger screen. This is too small. Let me change the screen right here. All right, so now we got this situation. We'd like to take a moment about 0.0. Again, remember, we're going to go ahead and we use this, our sign convention. To the right is positive, to up is positive, counterclockwise is positive. And the distance right here, let's say this is about 5 feet. And if I want to take a moment about this point, I'm going to take a moment this force, this force, this force. So let's go with F1. What I can do is say summation the moment about 0.0 is equal, counterclockwise is positive. First, F1 time the distance between this force and here. Remember, we talked about it. We said that m is equal F times d. And that d is a perpendicular distance. There is no perpendicular distance between this force and that. There isn't. They're on top of each other. So that distance perpendicular between this F1 and this 0.0 is 0. Or we could say in engineering that it's in the same line of action, so it cannot take a moment about itself right there. So m1, which is going to be, let me just go ahead and break it down, make it easier. m1 is equal m1 plus m2 plus m3. So m1 is equal f1 times d1, which is equal 40 times 0, and that becomes 0. Let's go to moment number 2, and that is this force here. The perpendicular distance between this force and this point is 5 feet. And here's the important part of it. It's rotating this way. So that force is going up like this and rotating this way. And this rotation is counterclockwise, so therefore it's positive based on that. We have up there our sine. We said, okay. So now we're going to say 75 times 5, and that's equal 375 foot-pound. Find M3, and our moment is this one. So we're going to find a perpendicular distance between here and right here, make it 90 degrees. What is this distance D equal? That's what we like to figure out. So distance D is equal, remember that's where the sine or cosine, we practice sine and cosine law. If this is a 5 feet, remember, so if we close it, it becomes cosine, but if you go this way, it becomes sine. So it becomes 5 times sine 30 becomes D. And therefore I can say it's equal 60 times 5 sine 30. And that's going to be really a minus. Let me put a minus here, because this is going to rotate this way. So this one is going to rotate kind of like that. And that's going to be clockwise, so it's going to be negative. So that came out to be 150 minus 150. And then we're going to come back and say our summation comes out to be equal. So summation moment about 0.0 counterclockwise is positive, and we're going to have 0 plus 375 minus 150, and that's going to give me about 225 pound-foot. So basically 225 pound-foot, based on our sign language, is positive. That means it's a counterclockwise rotation. That's all. It's just a counterclockwise rotation. And you learn in upper classes which rotation would you want to use for what. All right, so let me erase this book. We do another problem. Okay, look at this simple problem. We got this beam, pinned, and roller. We talk about that in future classes, what these means. So you got a 25 pound right here, 3 feet away you got 15 pounds, 6 feet away you got 10 pounds, 5 feet away you got 20 pounds, and then you get to the end of the beam. We'd like to know what the resultant force is. Remember, with all those resultant forces, well, that's easy. I can find the resultant forces. F of R is equal to summation of all F, F of Y, the all F of Y, so we don't have any F of X, and going this way is positive, which is equal. I got minus 25, minus 15, minus 10, no, plus 10. Plus 10 and plus 20. So that makes it, no, this is minus 20. Okay, let me see if I got that right. Minus 25, minus 15, plus 10, minus 20. So that's become 10, 25, 50. So I get 50 pound resultant force. Okay, fine. And that's down basically, or minus 50. Now here's the thing, why we're using a moment. Where is that resultant force? I'm going to show it like this. I got 50 pound. What does this mean? Basically this is saying that I'm just going to go ahead and recopy, hold this thing over here. I got this beam right here. One force here, one force here, one force here, and one force here. And you got this beam. Okay, this is equal. Same beam, but we're going to replace all these forces with one force. And we call that F of R. One thing you have to remember, in engineering, we're not going to go ahead and go through all this trouble, show this, show this. We're just going to come back and show 50 point, like a big different color at the dotted line, saying, you know what, if I replace all this, I can replace them with one. Or another way would be like this is 25, 15, 10, 20. So all this is equal this. Now, but I don't know where this force is, this distance x is what? Okay, that's where the moment comes in handy. I'm going to take a moment about point A, okay, and this one here. Not this one, just with the top. So I'm going to say, let me change color for good luck here. Summation moment about point A, counterclockwise is positive. I'm going to start from a further point and work that way. First start with 20. 20 is going to go this way. So this is what? This is clockwise. So it's equal minus 20. The perpendicular distance is 5 and 6 is 11. 11 and 3 is 14. Okay? And then I'm going to this force. This force is going up like this. It's going to be counterclockwise. So it's going to be plus 10 times 6 and 3 is 9. And then I'm going to come back here. This one is going to be counterclockwise, so it's negative. No, clockwise, so it's negative. It's going to be 15 times 3 minus 15 times 3. And this one cannot take a moment about itself because it's right on top of it. There's no distance between it. So it's equal. So it's 235 pound-foot. And now, that should, I'm going to use this one, take a moment about point A. A here, B here. So I'm going to go ahead and use the resultant force one. Moment about point A is equal. Counterclockwise is positive, so that's going to be kind of negative, minus resultant force, which came out to be 50, we calculated, minus 50 times x. So that's equal to 50x. However, whether you take a moment, all it is individual about this point, or you take the resulting, take a moment about this point, they should both come out equal. So basically I can say, okay, let me change color so you won't complain. 50 times x should be equal 235. Let's just say, but they're both negative anyway. There's a negative here, so I'm get rid of the negative sign. And therefore, x is equal 235 divided by 50, and that gives me 4.7 feet. So this distance right here is kind of 4.7 feet. That's where one application we could use it. It has a many application. So I hope this kind of warms you up, know what moment is. And let's do another example. All right, we're going to do one about uniform distributed load. Let me just show you. If I have a beam like this, and all the weight is like this, they call this a uniform distributed load. For example, weight of the beam itself is a uniform distributed, or weight of the concrete slab on top of the floor, uniformly distributed. Say this is each foot of it is about, let's say each foot of it is about 70 pound per foot. And this beam is about 10 feet. So we can replace this whole thing by one. This could be equal. I can replace it with one beam. It's kind of like that. Concentrated load. Put resultant force here, or just concentrated, not resultant force, concentrated load of this. This is a rectangular. The area of rectangular is what? Is length times height. The height of this rectangular is 70 pounds per foot. The length of it is 10. So this becomes 70 times 10, and that makes it 700 pounds. All right? These two basically equal. But in real life, we don't show it like this. The way we show it is like this. we're going to just put a dotted line right here, and we're going to say, okay, the concentrated load for this beam is 700 pounds. And the distance right here is, because it's a rectangular, the center of rectangular is the center of the whole shape, so it's 5 feet. Okay. Now, if this was let's do the same thing for which I've done many of these on my YouTube channel. You can watch it. What if we have something like this? Okay, let's make a triangle like that, and then your load is like this. And just put a beam under reaction underneath it, the support underneath it. So now, again, the concentrated force, and if we make, let's make this 20 pound per foot. Okay, so the concentrated force is going to be like this, someplace right here. And I'm going to, what's the magnitude is, what is the area of a triangle? The area of triangle is 1/2 base, which is 20 feet, time length. Let's say still make it 10 feet, time 10. So 10 times 10, I become 100 pound. The distance, and if you look at there's a shape which I show on a board right there. Each shape has their own center. The center of triangle is 1/3 from the base, is 1/3 of 10, which is 3.3.33, whatever. So this is how we do things. So let's do an example with the uniform distributed load in it. Let me erase this. Okay, so we got this beam right here. It's in a SI system, 3 kilonewton, 8 kilonewton, and this is 2 kilonewton per meter, 5 meter, 7 meter, 4 meter, 14 meter. Where is the resultant force is going to be? Whereas, say we're going to assume the resultant force for this going to be right here somewhere, not at the edge of this. I don't know where. Let me just take that out again. I didn't do a good job, not at the edge of it. My guess is it's someplace around here. Say it's going to be someplace around here. Okay, F R is equal what, and what is going to be either from this and from that, it doesn't matter. We can calculate that. So one thing we know is this is a uniform distributed load. And the concentrated load for this uniform distributed load, it's going to be 7 meter, center of here, and it's going to be right this. And that's going to be 2 kilonewton times 14. That makes it 28 kilonewton. So this is basically a concentrated load for this right here. This is the resultant force for all of them. So we're going to go ahead and say FR is equal summation of F, and they're all vertical, so I'm going to say summation FY, because all of them are vertical and going up is positive. And so I got minus 3 kilonewton, minus 3 kilonewton, minus 8 kilonewton, minus 28. And that's going to be 28 and 39. Okay, so we got 39 kilonewton right there. And then I'm going to take a moment about point A. Summation moment about point A is equal, counterclockwise is positive. I'm going to start from here back that way. I'm not going to count this. I'm just going to do all the forces, and I'll do that one later. So it's going to be the concentrated load for this one is going to be 28, and that's going to be going clockwise, so it's minus 28 times the distance is going to be from here to 7, and 7 is 14, 14 and 4, 18, 23 times 23. The next one is going to be right here, minus 8 times 12 minus 3 times 5 equal. Okay, minus 755 kilonewton. That's the moment about point A based on applied load. So what is the moment about point A based on resultant force? Okay, and it's just one force, and that's minus FR. Well, I'm not going to FR time that distance. I don't know this distance is what. I called X time X. But I know FR came out to be 39 minus 39 times X. And that really should come out equal to same as over there, which is equal minus 755. Minus cancel each other out. So X is equal 755 divided by 39. 19.4 meter. This is just to warm you up, get you going what moment is, but we will do million problems like this between now and you graduate, and then we on your own after that. But anyway, hope you like it. Don't forget the thumbs up, and if you're not, kind of subscribe. Encourages me to do more video. Have a good day.